Hello, this is Professor Matt Katroulis of Rio Hondo College, and this is the set of video lectures for Chapter 8 on acids and bases for our Chemistry 110 course at Rio Hondo College. The first problem that we confront when we're dealing with acids and bases is how we want to define them. There are at least 3 ways to define acids and bases, and we're going to look at a couple of those different terminologies here. So the first type of acid we want to talk about is called an Arrhenius acid, named in honor of Svante Arrhenius. And the definition of that is any compound which produces H+ ions in solution. Some people are tempted to call these hydrogen ions, but usually the terminology that we will use is proton. We will call those protons. Let's think about why. Remember that most hydrogen atoms do not have neutrons in their nucleus. So a single hydrogen atom would just be a proton with an electron floating around it. However, if it's an ion, it has lost that electron, and so all you have is a proton. And so that symbol works fine for describing protons. The opposite, if there is an opposite to an acid, would be the base. And so by the Arrhenius definition of a base, it is a compound that makes these ions in solution. And what do we call those? You'll recall those are called hydroxide ions. Another pair of definitions comes from Brønsted and Lowry. So the Brønsted-Lowry definition of an acid is a substance which donates or loses a proton in a chemical reaction. So that's not too much different from the Arrhenius definition, but it is a little bit different in that it's just saying it's not producing it in solution. It's just saying that anything that's losing a proton is an acid. On the other hand, a Brønsted-Lowry base is any substance which is going to accept the proton in a chemical reaction. So it's all based simply on the proton. So if something is losing a proton, it's an acid. If a chemical is accepting a proton, it is a base. For example, let's consider the reaction between hydrochloric acid and sodium hydroxide to give us water and sodium chloride. So here we have the chemical formula for hydrochloric acid and sodium hydroxide, and they make water and sodium chloride. Now, the sodium makes things a little bit inconvenient. It's what we call a spectator ion, in that it's really not participating in the reaction in any way. As soon as the sodium hydroxide is put into water, this dissolves. The ions dissociate, just like we discussed when we talked about electrolytes originally. And the sodium doesn't participate in the reaction in any way here either. All it's doing is keeping the positive charge balanced. So if we want to focus more closely on the acid and base, let's just get rid of the sodium ion for now and consider the reaction we have between hydrochloric acid and hydroxide ion. So what is losing or donating a proton in this reaction? Well, we have HCl in the beginning, and we have chloride ion at the end. So clearly this has lost a hydrogen, and its charge became one more negative. So it lost an H and a positive. It lost a proton. So hydrochloric acid is an example of a Brønsted-Lowry acid. Hydroxide, on the other hand, if we look at the before and after, so we have just OH minus here, and here we have the O and the H, but we've gained another H, and the charge has gone up by 1, from -1 to neutral. So the hydroxide is the base. It's the chemical which accepts the proton. Now, for convenience sake, we like to write protons a lot when we're writing out chemical reactions, but they do not actually exist in solution as free H+ ions. Instead, what happens is that they piggyback onto water molecules, and they form a species that we call the hydronium ion. So as soon as the H plus ion is formed, it jumps onto one of the water molecules that it's surrounding it and forms this species here, a hydronium. Now, that's a fairly reactive species. So what it does is it says, well, I don't want all these protons. So it loses one of these protons to another water molecule. And then that water molecule is now a hydronium ion. And well, that one doesn't want all three, so it passes the proton on. So what happens is it's kind of like a game of hot potato. No one really wants the extra proton, so it's constantly being passed around through the water molecules. So my preference is to write H plus rather than writing H3O plus. But you always have to remember that even though this is what we were writing down, in reality, it's always writing on a water molecule as a hydronium ion. Strong acids are strong electrolytes. Remember we talked about strong electrolytes and said that they were compounds which completely dissociated into ions in solution and are therefore able to strongly conduct an electric current. So what that means is that HCl, which is a strong acid called hydrochloric acid, it ionizes completely. So the proton is formed as one species and the chloride ion is formed as the other. By common agreement, there are 6 strong acids, and their formulas and names are given here. So the first 3 acids are what we call the hydroacids. These are all based on names that would end in "ide." So for example, chloride, bromide, iodide ions. So they all become hydroic acids. So hydrochloric, hydrobromic, and hydroiodic are all strong. Nitric, sulfuric, and perchloric, these all come from ions that would end in "ate." NO3 minus is nitrate. SO4 2-, you'll recall, is sulfate. And we haven't seen this one. ClO4- is called perchlorate. And you'll notice that the 8 becomes ic acid. So we have here nitric acid, sulfuric acid, not sulfic acid, but sulfuric acid, and perchloric acid. So let's take a look at these a little bit more closely. Let's say we had nitric acid here, and we wanted to ask ourselves, well, what does this actually form in solution? Well, since this is one of the strong acids, that means it's going to break up into its constituent ions. So the H becomes protons, and I'm going to write an equal sign here. I'm going to say, let's say that this is aqueous. Then that means it's really protons and nitrate ions. And of course, in reality, this is H3O+. If we wanted to have it as H3O+, we would have to show this as reacting with water, which is not something I like to do. I think that's kind of confusing. So I think this makes it a little easier to understand. How about hydrobromic acid? Again, this is a strong acid. So when we write this, what we really mean is that we have protons, which are really hydronium ions. And what's left over? Bromide ions. And even though you've never seen perchloric acid here, we can pretty much just follow the pattern to figure out what the ions must be. We have an H in the front, so that gives you a proton. and it gives you a perchlorate ion, ClO4 minus. Weak acids are weak electrolytes, and we didn't talk too much about weak electrolytes, but remember that the definition simply means that they only partially ionize. So that means if I have, hundreds of acid molecules, only a few of them might actually ionize. So that leaves you with a mix of mostly unionized molecules, but some ions. And those few ions are able to carry an electric current rather weakly, and that's why we call it a weak acid. So rather than giving a complete list of weak acids, which would be very, very difficult to do, we just want to say that any acid which wasn't on the list of the 6 strong acids should be considered weak. So let's look at some examples, but again, this is definitely not a complete list of all weak acids. So hydrofluoric acid, HF, is a weak acid. That simply means that in water, mostly what you have are HF molecules. Very few of them have broken up into protons and fluoride ions. Acetic acid, where we have the one acidic proton, it is this last one right here. Formic acid, we have one acidic proton, it is the last one here. You'll notice they are usually protons that come at the front, but when we get into organic chemistry, you'll see why we're writing these out this way. Carbonic acid is kind of a special case here because it's a very unstable molecule, and in water this almost instantly breaks up into water and carbon dioxide. And finally, phosphoric acid, H3PO4. It's very important to note that just because an acid is weak, that does not mean that it's not dangerous. Hydrofluoric acid is arguably the most dangerous of all the acids that I've shown on the slide so far, even more so than the other acids on the strong list, because its mode of action is very dangerous. So it can cause extremely deep burns and then can have other effects within the blood because calcium and fluoride ion bind so strongly together. And exposure to this can easily be fatal. So it's something that we don't want to mess around with. Just like we had strong and weak acids, we have strong and weak bases. So we have a similar definition here. A strong base is going to be any base which completely ionizes in solution. And the only ones that are going to do that are the hydroxide-containing compounds, which are soluble. Now, I did not give you an exhaustive list of all the different compounds which are soluble, so I'm just going to give you an abbreviated list of the strong bases here. They are essentially all the hydroxides from group 1. So that would be sodium hydroxide, potassium hydroxide, lithium hydroxide, and I did not list them here, but rubidium hydroxide and cesium hydroxide could be considered strong too. All of those are soluble because it turns out everything with an ion from group 1 is soluble in water. And most of the group 2 hydroxides are strong bases. Barium hydroxide, certainly. Most everyone considers strontium hydroxide also to be a strong base. Calcium hydroxide is a bit controversial. It is just barely soluble in water. And because it's just soluble enough, a lot of us consider this to be a strong base, but that is open to debate among chemists. What we all do agree, though, is magnesium hydroxide is not a strong base. It is actually a weak base. So it is clearly not on this list. nor would be aluminum hydroxide from group 3. Ammonia is a rather special molecule that we want to consider when we're talking about bases. If ammonia is placed in water, and recall ammonia is a gas, so we would be attaching a hose to a container of the gas and bubbling that gas into the water, it is extremely soluble in water, and the gas will start to dissolve readily into it. And a very small amount of the ammonia will react with water. And when it does so, it will form ammonium hydroxide, or ammonium ions and hydroxide ions. You'll notice this is an acid-base reaction, specifically a Brønsted-Lowry reaction, because the ammonia, the NH3, is accepting a proton from the water. This makes ammonia a base, and in this scenario, water is acting as an acid. So when we talk about ammonia solutions, we often see them labeled as ammonium hydroxide or with the words ammonium hydroxide, but the real truth is that it's mostly ammonia molecules simply mixed in with water molecules. So this is still a base, but is it a strong base or a weak base? Well, if it's mostly these uncharged ammonia and water molecules, and very few ions actually exist in the solution, this would have to be considered a weak base. For the time being, we're not going to consider any other weak bases than ammonium hydroxide. And if we wanted, we could add magnesium hydroxide and aluminum hydroxide to that list as well. But they are probably the most difficult of the compounds to come up with a comprehensive list of the weak bases. So to summarize, the types of strong electrolytes are the strong acids, the strong bases, and as we saw when we talked about electrolytes in Chapter 7, soluble ionic compounds. The weak electrolytes are mostly going to be weak acids and weak bases, and occasionally we add to that list very, very slightly soluble ionic compounds, but for right now we're just going to limit ourselves to these lists right here. And then non-electrolytes are going to be the covalent compounds which do not ionize at all. And so these are not acids or bases, they simply dissolve. Typical examples are alcohols, which are things like methanol, ethanol, isopropyl alcohol, and carbohydrates or sugars. And insoluble ionic compounds are typically treated as non-electrolytes because if these compounds do not dissolve at all, then they do not dissociate, they do not form ions, and therefore they should be considered as non-electrolytes. Let's extend our understanding of Brønsted-Lowry acids and bases a little bit further. So we saw that a Brønsted-Lowry acid loses a proton, and what is left over after having lost that proton is called the conjugate base. That's because if the reaction were to go backwards, what would that compound be doing? The product would be gaining the H plus back if we went backwards. And so that's why it would be considered a base. It would be accepting the proton. Conjugate simply means it's on the other side, which will always be on the right side of the equation from our perspective. So a Brønsted-Lowry base gains a proton in a chemical reaction, and the substance that's formed after it's gained that proton is called the conjugate acid. Again, that's because if the reaction were to go backwards, instead of gaining the H+, it would be losing the H+. It would be acting as an acid. So let's see these terms in context. So here I'm showing a reaction between the strong acid, hydrobromic acid, hydroxide ion, which could be coming from sodium hydroxide or potassium hydroxide or any of the different compounds out there that we looked at that give us hydroxides, is making water and bromide ion. I am showing this right now as an equilibrium. In reality, the equilibrium lies extremely far to the right, which means that almost none of the HBr will remain. It's almost all converted to water and bromide ions by the end of the reaction. So which chemical is the acid? Remember, we're always going to consider the acid and the base as being on the left side, and the conjugate acid and the conjugate base as being on the right side. So the acid must be one of these two compounds right here. They both have hydrogens, so I can't use that as my sole means of determining which of these is the acid. I have to say which of these has lost an H plus when I look at the end of the reaction. So let's look at HBr first. Well, we have here a Br minus, so this is what would be left over if HBr lost a proton. It would be bromide ion. So that means that hydrobromic acid is, not very surprisingly, the acid. Which substance is the base? Well, by elimination, if HBr was the acid, hydroxide would have to be the base. And let's ask ourselves, is it accepting the proton? So do a before and after picture. We have hydroxide before, and at the end we have water, H2O. It has gained an H plus to form water. So hydroxide is the base. Which substance is the conjugate acid? The conjugate acid is essentially the base plus the proton. So our base here gained a proton and made water. That means this is the conjugate acid, because if the reaction were to go backwards, it would lose that hydrogen again. So it would be acting like an acid. And which compound is the conjugate base, or in this case, which ion? It's essentially the acid after having lost the proton. So this was the acid. After we take away the proton, we have bromide ion. This is the conjugate base. If the reaction were to go in the left direction, it would have to pick up a proton. Okay, I would like you to pause the video as soon as I'm done with these instructions, and I want you to label each of these reactions as to the acid, the base, the conjugate acid, and the conjugate base for each of these. Remember, you need to consider the before and after picture usually to determine which of these is the acid and which of these is the base. For example, it is possible for an acid to behave like a base in one of these reactions. So we can't just look at this and go, oh, that's definitely the acid, or oh, that's definitely the acid. You need to look and compare what do you have before the reaction and what do you have after. So go ahead, please, and pause the video. And if you only want to do one of these at a time, that's fine. And identify the 4 different compounds in solution here. And then we will resume. All right, I'm assuming that you have at least done this first reaction here. So let's start by identifying the acid. Just looking at these formulas, either of these could be the acid because they both have a hydrogen in them to donate. So if HCl loses a proton, we'll have Cl minus, which we do. So that means this is the acid. On the other hand, if this had been the acid, it would have lost the H plus, and that would have given us SO4 2 minus, sulfate ion. There is no sulfate ion by itself over here. So therefore, hydrochloric acid is the acid. that would mean that this compound here has to be the base. And this is the bisulfate or hydrogen sulfate ion. And in fact, if you do compare, it has gained H+ to form H2SO4. So the base forms the conjugate acid. Right? Think about this. If this compound loses a proton, it's acting as an acid, it forms the base. And then by process of elimination, the chloride ion would be the conjugate base. It can only be a base because there are no hydrogens for it to donate. All right, if you haven't attempted this question, please pause the video. Assuming you have, let's go ahead and continue here. So here I have carbonate ion plus ammonium ion making bicarbonate ion and ammonia. So let's first find the acid. In this case, the acid has to be ammonium ion because carbonate ion doesn't have any protons on it. So if it has no protons to donate, it cannot be an acid. It cannot be at least a Brønsted-Lowry acid. So the acid is the ammonium ion. That would make the carbonate ion the base. So the conjugate acid is what you get after the base has added an H+. And so you'll see here we put an H in the front, and this went from 2- to 1-. So therefore, this would have to be the conjugate acid. And again, by elimination, that leaves ammonia here as the conjugate base. Neutralization reactions are essentially most easily understood as the reaction between Arrhenius acids and Arrhenius bases. And so the general form of this reaction is an acid plus a base gives you water and a salt. If you try to use a Brønsted-Lowry acid or base, you don't always get water, which is why we mostly want to keep this in the context of Arrhenius. A salt is essentially any ionic compound, although technically hydroxides are not ever considered salts. So even though sodium hydroxide is an ionic compound, it's considered a base rather than a salt. The most important part of the reaction is this. The protons come from the acid, the hydroxide ions come from the base, and whenever they combine, they make water. And this is why it's called neutralization, because an acidic and a basic compound forms one that we consider to be neutral. So let's look at a couple examples here. So we have hydrobromic acid plus potassium hydroxide forms water, and then the salt is just whichever ions are left over. So the positive ion left over is potassium, and the negative ion is bromide, so potassium bromide. Here I have nitric acid reacting with barium hydroxide. It's forming water and a salt. The salt is barium nitrate because the positive ion here was barium and the negative ion was nitrate. So let's practice with a couple of reactions here. So I want to look at the neutralization of lithium hydroxide by hydrobromic acid, and then the reaction of sulfuric acid with strontium hydroxide. I'm going to go ahead and go over to my notes view to write these out, although I did not prepare any notes for this chapter. Okay, so we want to start off by writing the acid and the base. You can write them in either order, but I usually prefer to write the acid first. So I know that lithium hydroxide is a strong base, and hydrobromic acid is a strong acid, so it makes sense to write the acid first. So I have here HBr plus lithium hydroxide. Lithium is +1. Hydroxide is always -1. It's not a very nice H. It's not much better. But anyway, it would be LiOH. And acid plus base makes water plus salt. And what's the salt here? So the positive ion over here was the lithium ion, and the anion was the bromide. So this would give us lithium bromide. If we were to write the states for these, hydrobromic acid would be aqueous. Lithium hydroxide would also be aqueous. All these strong acids and strong bases are. Water is a liquid. And lithium bromide, you would have to know whether it's soluble or not. It turns out it is, so it is going to be aqueous. In general, though, I'm not going to require you to write states in this class. Are these chemicals balanced? It looks like it. There's 2 hydrogens, 1 oxygen, 1 lithium, and 1 bromide. Okay, the next reaction is sulfuric acid with strontium hydroxide. Sulfuric acid has formula H2SO4. It is aqueous, but I'm just going to leave that out for this reaction. Strontium hydroxide. Strontium is in group 2. So that means we would need 2 hydroxide ions because they are only -1. So acid plus base gives you water plus salt. So the salt here would be strontium, which is 2+, coming together with sulfate, which is 2-. So this would be SrSO4. Are we balanced? Almost. You'll notice that there are 4 hydrogens on the left side. 2 plus 2 times 1 here is 4. So we need a 2 here. And how about oxygens? Well, we've got 1 sulfate and 1 sulfate, so those oxygens and sulfur are taken care of. These oxygens, we have 2 of them, and we have 2 of them. So yes, we are balanced throughout. I am not going to write the states here, but they would be aqueous, liquid. Strontium sulfate, it turns out, is solid, but you have no reason to know that, and it's not something I'm going to require you to know. So this is going to be the end of the first video for acids and bases. And when we come back in the second video, we're going to look at these from a more quantitative perspective and start looking at how to calculate the molarities of the important ions, like the protons and the hydroxides that figure into acid-base reactions. Thank you.